Now let's look at the case where the denominator has some repeated linear factors, or maybe a mix of factors which are repeated and some linear factors which are non-repeated. So for every factor of type aix plus bi to the k, that is a linear factor to the power of k in the denominator, in the partial fractions decomposition of this rational function, we'll include one term for every power of this linear factor from 1 through k. So we'll include a term of the form a1 over aix plus bi, plus one of the form a2 over aix plus bi squared, etc., plus one of the form ak over aix plus bi to the k. And this gives us k distinct terms for every linear factor of the power of k in the denominator in our rational function. Here's an example. Suppose I want the partial fractions expansion of the rational function x cubed plus 2x plus 2 over x minus 2 cubed times x minus 1 squared. This is a proper rational function. The degree of the numerator is x cubed and the degree of the denominator is 5. So according to the above prescription, the partial fractions decomposition should look like this. For the x minus 2 cubed in the denominator, I'm going to include one term for every power of x minus 2 from 1 through 3. So I'll have an a1 over x minus 2 plus an a2 over x minus 2 squared plus an a3 over x minus 2 cubed, where a1, a2, and a3 are constants. There are some real numbers that I have to solve for. And for x minus 1 squared, I'm going to include an x minus 1 term and an x minus 1 squared term. And they appear as b1 over x minus 1 plus b2 over x minus 1 squared. And notice that we could integrate all functions that look like these terms of this partial fractions decomposition using logarithm or integration of powers, very simple techniques. Let's try to integrate this particular function, 2x plus 4 over x cubed minus 2x squared. Our partial fractions decomposition, we factor the denominator here into x squared times x minus 2. We have one repeated factor, x, or x minus 0, which is squared, and we have one factor which is not repeated, x minus 2. We include one term of the form c over x minus 2 for that non-repeated factor, and for the repeated factor x squared, we include two terms, a over x plus b over x squared. So our rational function 2x plus 4 over x squared times x minus 2 should be equal to something of the form a over x plus b over x squared plus c over x minus 2. And our job is to solve for the a, b, and c. The first step of this process is always to multiply by the denominator on the left-hand side, the denominator of our rational function, and cancel whatever we can on the right-hand side and on the left. So multiplying by x squared times x minus 2 on both sides of the above equation gives us 2x plus 4 on the left-hand side is equal to a times x squared times x minus 2 over x plus b times x squared times x minus 2 over x squared plus c times x squared times x minus 2 over x minus 2. Now we cancel whatever we can on the right-hand side. On the left-hand side, we're left with 2x plus 4, just the original numerator. the first term on the right-hand side, an x will cancel. We're left with a times x minus 2. In the second term, an x squared will cancel. So it becomes b times x minus 2. And in the third term, the x minus 2 cancels, so it becomes c of x squared. And now using this single equation, we want to solve for a, b, and c. Remember, this is true for all x values. So we could use some special values of x to find some of these constants a, b, and c straight off the bat. So plugging in x equals 0 will make two of those terms on the right-hand side equal to 0, and you'll get b times minus 2 equals 4, or b is equal to minus 2. Plugging in x equals 2 will get rid of the first two terms on the right-hand side, and you'll have c times 4 equals 8, so c must be equal to 2. Now you could substitute those values for b and c, and then maybe substitute some other value for x to find a. That's one way of approaching it. The other is to compare coefficients. So the first step of that would be to expand everything on the right-hand side, gather up the coefficients of x squared and the coefficients of x and the constant term, and the right-hand side becomes a plus c times x squared plus b times minus 2ax minus 2b, and that always equals 2x plus 4. And as I mentioned before, when two polynomials are equal, then the coefficients of the powers of x have to be equal. So the coefficient of x squared on the left is 0, so a plus c has to be 0, and the coefficient of x is 2, so 2 has to be equal to b minus 2a, and the constant term on the left is 4, so we have minus 2b equals 4. Now immediately you can solve for b here, and you can write a in terms of c. So using minus 2b equals 4, we get b equals minus 2 straight off the bat. And plugging that into b minus 2a equals 2, we get minus 2 minus 2a equals 2, or minus 2a equals 4, and a equals minus 2. And now, of course, a plus c is 0, so c has to be equal to minus a, which is 2. So you have options on how you're going to solve for the a, b, and c, and when you've solved for them, you've now broken up your rational function into its partial fractions decomposition. 2x plus 4 over x squared times x minus 2 is minus 2 over x plus minus 2 over x squared plus 2 over x minus 2. And you could add these fractions on the right just to check that this is in fact true. Now the integral of our rational function is 2 times the integral of 1 over x dx, which is very easy, minus 2 times the integral of 1 over x squared dx, which is also very easy, plus 2 times the integral of 1 over x minus 2 dx, which is also very easy. So these integrals are minus 2 times the natural log of the absolute value of x. Using the power rule for the second one, we get plus 2 times x 1 over x, or x inverse, plus 2 times the natural log of the absolute value of x minus 2 for the last one, using a substitution, u equals x minus 2.